This group is chaired by Professor Taifu Lin. Taifu has shown great leadership, reviving the SG and bringing the activity back. So I want to really thank Taifu, use this opportunity to say great thank you to Taifu and his leadership for bringing us back together. We also have several of our members that have been with us for a very long time, from Barcelona, from Denmark, which are going to present, from Sydney, and also new members from the US. So it's actually great to have each other here and work together. So this is a series of webinars we are starting under Taifu's leadership and with the committee to share knowledge between the group and learn about what's new in the field of algal toxins and taste and odor compounds in a very large gamut of environments. It's all related to water, but different applications. And also, hopefully this will lead to us as a community coming back together again, working closely together, build new collaboration. As it was mentioned, these webinars are recorded and will be shared with all, so please share the link. And also, before we start, Taifu, maybe you will put at the end, the specialist group is also organizing is it at our 12th conference or 13th?
I need to open another file.
Or maybe you can mention that at the end, Taifu, but we are also organizing our committees. So our special group as conference later this year, mid this year in Shanghai, and Taifu can share that information. So this is really amazing progress. So before further ado, we are going to have two great speakers for this webinar. Professor Niels from Denmark. I think, Niels, you've been with the SG for a very, very long time. You're one of our longest standing members, so it's a great honor to have you. Do you know how many years you've been in the SG?
Many years.
And now is going to talk to us about taste and other compounds in the aquaculture industry, production and removal focus on aquaculture system with water recirculation. It is a great honor to have you with us. Here you have a little bio of Niels, who has been serving the water community for a very long time, and also there's a link to your website from the university in Denmark. And once Niels is presented, we will have a presentation from Hunter Adams. Taifu, you want to go to the next slide, please? Thank you. Hunter is a new member of our SG, I think. Is that correct, Taifu?
Yeah.
Yes, and Hunter is he's going to talk about identification of unknown taste and other compounds in water treatment processes using recent advances in sensory and analytical techniques. Hunter is based in Texas, and he is very, very active. I'm very, very impressed, Hunter, with the publications that you have recently, the LinkedIn ads, and I have the honor of working with Hunter on the renewal of American Water Works Association Algal Management book, M57. So, and it's 6 or 6:30 a.m. in Texas. So we are the both end of I'm finishing, and you start. So I'm talking to you from the future, Hunter. The future is brighter than we think. So with that, I really thank the speakers for their times. And now we start with Niels. Niels, you want to share? Before Avalsha, Niels is sharing his screen. Taifu, did I miss anything? Or so this is the agenda. That's actually good. Perfect that you put it up. So this was the short opening to welcome everybody and have this opening now. We will start with Professor Niels, and then 30 minutes is your talk. Then we will have Hunter for 30 minutes, and then discussion that will be led by Professor Taifu and Jianwei. So this is amazing. Taifu, did I miss anything? Would you like to add anything? All good. So Niels, if you would please kindly share your screen. The online podium is yours.
I will do my best to see if it works this time.
No, I'm sure it will.
Can you see my screen now?
Not yet.
Not yet. Yes, it's coming up. It's coming up. Ah, yes, we can see the screen now.
Yes, yes.
Okay, thank you. So you can see the screen and you can hear me?
Yes, very clear.
Okay, very good. So I will give you a presentation. I have 25 slides. I will do it in less than 30 minutes, I hope. And my topic maybe is a bit different from what your interests are, but maybe you can still find some interesting points. So it's about fish production with recirculation of water. And when you search Web of Science for articles on recirculation and aquaculture, you can see that the first publications they came out in the 1970s, and then the number has increased over the recent years, meaning there's a research interest in recirculation in aquaculture. But if you also look at fish and off flavor on Web of Science, you can see that since the early 1950s, there has been publications on the off flavor in the aquaculture industry. So there's definitely an interest both in recirculation and in off flavors in fish production. I will use Denmark as an example on the change from simple fish farming to advanced industrial fish farming today. Here's a typical farm in Denmark about 25 years ago. When you used stream water, you had flow through, meaning the water was used only once. Here are the feed containers. When the fish touch a little pin here, feed will fall out. Then about 10 years ago, more and more systems with water recirculation were introduced. It was typically well water used for as water source, could also be stream water. But today, the new facilities being built in Denmark, they are industries where high investments and full-time workers are employed, but still they use well water and sometimes seawater. So the change has been from many times just a hobby activity producing fish to an industry today and using recirculation of the water. Here's a plan of a typical fish farm with water recirculation. You have the fish in the tanks here in the middle. The water is recirculated, so every hour the water is coming back to the fish tank. First, the water enters a mechanical filter that removes particles larger than maybe 50 micron. It's called a drum filter. Then the water is passed on to a biofilter where there are several units where you have these little plastic chips. They are about 1 centimeter large. In each unit, you have about 1.5 million of these little plastic devices. The purpose here is to oxidize ammonium to nitrite, but also remove organic matter. And you bubble through typically just air, but it keeps the biofilter aerated. Then the water is passed on in some systems to an ozone unit. The purpose is to reduce traces of organic matter, but also to kill bacteria if they are present. Then you remove bicarbonate and CO2. You don't want too much CO2 in the water. That will make the fish sleepy and they will not eat. And then from that last treatment, the water is transferred back to the fish tank where it's oxygenated with pure oxygen. And then the water is circulated back once more after about 1 hour. And you have feeding systems, as you can see here. These units are sold as turnkey units where companies offer to set up the entire system. So you only have to get fish and feed, but of course also maintain the system. So what are the differences between traditional systems and recirculated systems? In the traditional systems, you had a high water consumption. You discharge nutrients in natural waters. And because of that, the environmental politicians in the European Union, they encourage fish farmers to change to systems using less water and improve the water treatment. So that has led to construction of the recirculated systems, the RAS systems, where you circulate, reuse water. Every day you add maybe 1, 2, 3% of new water. You can have a high biomass in a restricted volume, which makes it profitable for the fish farmer. The feed utilization is typically high because you have many fish in a small area and they will eat all of the feed. You don't have any external input of pathogenic organisms from seawater or freshwater. You can control the waste, also reduce spreading of diseases. But it seems that all flavor producing bacteria, they grow happily in these recirculated systems. And that has caused a lot of problems for people who bought these turnkey industries, because they expected to produce tasty fish, but they end up producing fish that they cannot sell. And often when you have these off flavor issues, fish farmers could spend up to 10% of their profit on reducing the off flavors. I will come back to how you can do that. And also for buying these RAS industries, you need a lot of money, so it's quite an investment to the fish farmer. In Denmark, we have about 50 RAS farms for freshwater fish. It's mainly rainbow trout, but also one large indoor system for pike perch. Pike perch is an expensive fish compared to rainbow trout, as you can see the rainbow trout here. And we have new farms on marine fish for land-based production. 3 of them produce Atlantic salmon, and 1 is producing yellow-tailed kingfish. And the last one, the kingfish, is produced in warm water. The Atlantic salmon is produced at temperatures not higher than 15 degrees. Off-flavored fish is not a new invention in fish farming. I found this website from a major pangasius producer in Vietnam, and on the website the producer notifies that the fish do not have muddy taste and they have no off odor. And I would say it's special to sales arguments to underline that this fish is not bad tasting. So it is an international problem when you produce fish at high intensities that you get off flavors. The typically studied off flavors are jasmine and 2-MIB. You are all familiar with that. But when we analyzed some of the pike perches, you can see the fish in the middle here, for content of various organic compounds, there was a lot of aldehydes, benzenes, terpenes, sulfur compounds, alcohols, and ketones. Many of these compounds have positive flavors, but some of them have also rather nasty tasting flavors. So and of course a fish has some natural taste as well. But there's a tendency that terpenes are often found, many of them with woody flavor, or aldehydes, some of them with rancid flavors, and they don't contribute very well to a tasty fish. So where do the off flavors come from? Since fish in RAS are typically fed feed only and no other feed components, you might expect that the feed and the feed ingredients are a main source of the off flavors, and this is correct. But sometimes we can find organic compounds in the feed that is not found in the fish. We have one example with fish from Bangladesh where an alcohol was the most common organic volatile compound in the feed, but we could not find it in the fish, most likely because it is metabolized in the fish. So feeds is one source, then algae and bacteria in the water could also be the biofilter, is another source because the bacteria produce the off flavors. And then the fish themselves could produce off flavors typically from oxidation of various fatty acids as shown here. It could also be bacteria in the intestine that metabolizes feed ingredients, producing some unwanted compounds. If we look at two different environments, if it's outdoor systems and there are nutrients and light present, it will typically be cyanobacteria producing the off flavors. You can see here an example from a Danish outdoor fish farm where on the concrete wall there are cyanobacteria growing. I was setting up a little transparent plastic box on the side of the wall, and after it was clean from start, after 2 weeks it looked like this, and the geosmin content was about 20 times higher inside the box than outside the box. So it's obvious that cyanobacteria growing on the surfaces in outdoor systems, they produce at least geosmin. If it's indoor systems and you have organic matter and also oxygen in most cases, we have mainly focused on actinobacteria like Streptomyces. It's filamentous bacteria, as you can see here, and there are several publications on this. But recently we have started looking at another group of bacteria named myxobacteria or slime bacteria. We find them in biofilters in all the RAS systems we have looked at. They have not been cultivated to any extent because they are difficult to grow, and one reason is that they are predatory. They feed on other bacteria, meaning that they are difficult to grow in the laboratory. But the myxobacteria we have isolated from RAS farms in Denmark, they all produce geosmin. So we believe that these bacteria, myxobacteria, because they are common and because they form a slime layer on the surface of the bioelements, that they could be the most common producers of off flavors. Just to emphasize that feeds could be a source of volatile compounds in fish. Here's a result from a German study where 4 different feeds were tested by a sensory panel, and the sensory panel, they must have been very good. They identified more than 80 compounds in the 4 feeds, and 55 of them were common to all 4 feeds. And here is a list of some of the compounds. But you can see that the feeds had typically fishy flavor, maybe cooked potato flavor, sometimes mushroom flavor. So there's definitely a taste component in the feed as well. And the Germans write that the lipid source could be one reason why you have these flavors. Could also be some fatty acids, or it could be the protein, depending on whether it's plant-based or fish meal-based protein. So there are many sources of off flavors. I should also mention that fish feeds can be oxidized when you store them for a long time, so that could add an additional flavor ingredient. I will give you a couple of examples on episodes of geosmin in a Danish system. Here it's producing this pike perch. We have a number of tanks, grow out tanks, as you can see here. The water is passed through a drum filter, where part of the water is UV treated, another part is treated in the denitrification unit, and then the water is passed onto the UV filter. But all the water ends up being led into 4 biofilters, and after the biofilters, the water is aerated in trickling filters, you can see here, and part of the water is circulated back to the denitrification unit. So that's the system we analyzed. And I will not go a lot into details here, but just show you that when everything is running smoothly, you can have a constant level of geosmin, as shown here in the grow-out tanks. Only at the outlet of the denitrification unit, you had an increase. But when you start cleaning the biofilter, I think you do that every second week maybe. You from start you have a level of about 10-20 here, but when you start cleaning the biofilter and you do that by shifting between washing and aeration, you can reach up to 100 nanogram geosmin per liter, and it takes up to half an hour before you're back at the initial level. So if this high amount of geosmin is transferred into the fish tank, that fish can take up through the gills the geosmin and other off flavors, so that's the risk. Also, just when you clean the denitrification unit, you can see you get these little bursts of geosmin, and it's even worse in other cases. Here you can see what happens when you clean the biofilter. This is at another date than here. Here you, after cleaning, you get more than 200 nanogram geosmin in the from the biofilters, and the water is passed on to the tanks. So the fish are exposed to a high load of geosmin, and the same here. This is for the denitrification unit. So the lesson to be learned from here is that when you treat the biofilter, you should be careful not to let the water pass into the tanks before some time has passed. Another example is a long-term study, 3 months from an outdoor system in Denmark. It consists of 12 tanks, and it's for rainbow trout. Each tank is about 20 meter long, 6 meter wide, and at each end of the tank there are 6 biofilter units, as you can see here, and each of the 6 biofilter units has about 1.4 million of the little plastic beads. We'll analyze the geosmin content from mid-July to end of October, and you can see that we could reach an average level as indicated here, about 10.5. Then we determined the number of potential geosmin producing bacteria on the biofilter elements using quantitative PCR. So each GEO gene represents, we expect, 1 bacterium producing geosmin, and on each of the little 1 centimeter bioelement there was this amount of bacteria producing geosmin. And if we look up in literature how much geosmin can 1 bacterium produce and relate it to the number of potential producers, we get this number here that every day per liter this amount of geosmin could be produced. So when we have about 10 nanogram per liter in the water, you could see that this amount could easily be produced within a few hours. And this is just bacteria sitting in the bioelement. So we believe that the bioelement, again, they are the most important producers of geosmin. We also looked at geosmin and 2-MIB in the fish. And for geosmin, the level was very high. It should not be higher than 250, 300. So they will need to depurate the fish. For MIB, we were closer to the limit. But it shows that, I think most important message here is that in a large commercial RAS farm, you can keep a rather low level of geosmin. These spikes in geosmin here and here, it's uncertain why this happened, but we might find out one day. Then if we look at correlations between environmental parameters and geosmin in the water, we did not see any correlation between phosphate, ammonia, nitrate, pH, and so on. But there were some correlations in the water. So the red color indicates a correlation. So if you look at geosmin in the water and geosmin in the fish, you can see when there's more geosmin in the water, sorry about that, there's more geosmin in the fish. And at the same time, if there are more geosmin in the fish, there are also more 2-MIB in the fish. But otherwise, we could not see any connection between changes in ammonia or phosphate or pH and the concentration of geosmin. So that's it still leaves open space for more research. It can sometimes go very wrong. This is a result from a Danish salmon farm inland salmon farm that started maybe 10 years ago. And for start, they used water. See the time here and the adjustment content in the water. They used water from a local fjord with brackish water, and that was not a good idea. The water in the tanks 1 and 2 here was very high, and it even after about 40 weeks, the concentration of jasmine was quite high. The blue, that's the drum filter, but the water level in the tank, that is the most important. So the company could not sell the fish, and the investors were getting desperate because they spent a lot of money in the system. So be careful what the water source is when you start a recirculated system. What you want is a level not exceeding maybe 10 or 15 nanogram per liter as shown up here. So if you have a lot of off flavor in your fish, what can you do? You can depurate the fish, and your aim for that will be to reach a level of for jasmine about 250 nanogram. Here's an example from depuration of pike perch, where the fish had from 600 to maybe 900 nanogram per kilo. That's too high. And this is the first day of depuration. This is 2 and 1 day ahead. So the fish were depurated in clean well water, where I think half of the fish tank water was emptied every day, and then you fill up with another half of the clean water. And you can see that after 7 or 8 days, you have reached an acceptable level for your jasmine, about 200, 250. So there's no reason to continue any further. From the dilution at start in the water, you can calculate what would the concentration of jasmine have been in the water. You can see here. But because jasmine is released from the fish, you get a higher concentrations in our case. So it's a good confirmation that the depuration is working. There are some challenges when you depurate fish. You need separate tanks, and tanks are expensive to build. You need sufficient water. It should be clean. It takes labor, man hours to move the fish. You cannot feed them because you don't want bacteria to grow up. It means fish lose weight, and the farmers lose income, 10% each year. And also there's animal welfare considerations because the fish are left without food for a number of days. So I think what you should do, try to keep the water as clean as possible, optimize your biofilter function, don't feed too much, and also maybe apply some treatment for keeping the jasmine level in the water at a low concentration. Some of the, I think on my clock, almost 20 minutes has passed, but I think we'll be in due time here. So some of the procedures you can use, and they will be familiar to all of you, is treatment of the water to reduce jasmine with particulated activated carbon. You can use advanced oxidation procedures. You can use nano bubble or micro bubble technology. I don't think it was ever a success because you could not detect if it was dissolved oxygen or nano bubble oxygen. The nano bubble should be quite reactive, and that was popular some years ago. I don't think it's in focus at the moment. But one technique I know is being introduced is vacuum UV lamps. You can read the details later if you want. The new thing about vacuum UV lamps is that they have an intense wavelength at around 185 nanometer, in addition to the traditional 255 nanometer. And when you use it in AOP, the low wavelength will ensure that you get reactive hydroxyl radicals shown here. And if you combine these radicals with conventional UV hydrogen peroxide, you can reduce the amount of hydrogen peroxide, which is unwanted in a fish farm, meaning that you can have an efficient water treatment. But this technique, although it's new, it seems quite promising. And this company, I have to admit, it's a Danish company, but they just built a huge facility in Brazil So they think this could be one new way forward. And an advantage is that it's very good at converting electricity to UV light with a minor consumption of power. You could also use microbiology for removing the ore flavors. This is a study from Israel where they used bacteria isolated from sludge in a rice farm, and the bacteria they isolated, they could actually grow using jasmine or MIB as the only carbon source, and you didn't have to have oxygen, but if oxygen was present, that was also nice. We have contacted these researchers and asked if we could have the bacterial cultures, but they said, no, we don't have them anymore. We have lost them. Recent studies indicate that in the drinking water industry, you can also use bacteria, maybe bacteria isolated from water treatment plants to reduce at least jasmine or MIB. But the concentrations used in these studies are typically very high, and it's a slow process, so you would not use it for any commercial industry. More curious example that I was involved in is uses of snails that graze the bacteria, eat the bacteria that produce the ore flavors. And we could see that when you added this little snail here to tanks with rainbow trout, then in the oxygenation unit, we could reduce the number of the jasmine producers. You can see the jasmine producers here without snails and with snails, and the content of jasmine in the fish was significantly lower when we had snails in the water. But fish farmers don't want snails in the water because they produce mucus, which form bubbles, so that's not wanted. Then the final approach we have tested here was trying to find out when is jasmine actually produced. And we believe that all jasmine producers, they have the GEO gene that encodes jasmine synthase. And in a myxobacteria isolated from a Danish rice farm, we inserted an M-cherry gene that produces red fluorescence. It was inserted in the genome just in front of the GEO-A gene. So when the cell is producing jasmine, it is emitting red light. You can see the red color in the picture here, and it worked very well in the laboratory. We hope it will also work well in the real system, but that would give us a unique opportunity to detect when jasmine is produced. Is it phosphate? Is it ammonium? Is it some organic compounds? We can find out about that perhaps. Then the final slide here. So what do you do in the future when you have ore flavor problems in rice farms? You could try and control the microbial activity in the biofilters. Don't overfeed. Keep conditions such as temperature and nutrient removal at the optimum level. Maybe treat the water to reduce ore flavors. That could be advanced oxygen processes. And also when you depurate the fish, be sure you do it at an optimal condition so you don't harm the fish. The fish don't look happy when you have kept them for 3 or 4 days without feed. They start becoming inactive. And also we had animal welfare. There's a little summary in the last slide here if you want to read it. So those were the words from me. Are there any questions that we look at some of the slides again? Otherwise, I will turn off the sharing.
Thank you very much, Professor Niels.
Okay, so now we should be back at usual.
Right. Yes. Okay. Now we're back to the screen. So because we will have a discussion after the second presentation, so may I, request that we can start our second presentation first, and we'll come back for discussion.
Yep, that's fine with me. I'll mute myself now.
Thank you very much. This is good. Excellent. Thank you for your nice presentation. So now our second speaker will be Hunter. So Hunter, I'll allow you to control the screen.
Great. Can y'all see that?
Yep. Very clear.
All right, great. Good morning or afternoon or evening, wherever you are in the world. It's 6:30 a.m. here in Texas. So I've got my coffee ready with me and I'm ready to go. That first presentation was great. A lot of interesting things that I typically don't think about in the water treatment industry, but there's a lot of overlap between that and mine. So we'll run through here. I'm going to talk about what is available in standard methods for the examine of water and wastewater first, and then we'll look at how we use that in our system, and then how we've used some of these methods to identify some uncommon taste and odor compounds in our water treatment processes. So some pretty cool stuff that we're doing. I want to thank my co-authors, Mark, my boss, he's our utilities manager, Sam and Emily work in our lab, and Keisuke Ikehata, he's on the call today. He's a collaborator from Texas State University who's a water reuse expert and working with taste and odor and aesthetics as well. So we do a lot of cool stuff between our two labs. So real quickly, who am I? AA water and wastewater operator. I've got a graduate degree in biology. I never thought I'd do chemistry, and then I do organic chemistry, basically for a full-time job now. So life's funny like that. I ran the lab here for 10 years, and for the last year, I've been the superintendent in charge of the water systems operations, maintenance, and the lab for 5 source lakes, 5 conventional treatment plants, an advanced treatment plant, and the water towers, ground storage tanks, pump stations, and the conveyance system. So a lot of cool stuff we do here. I'm very involved in the water industry. I just realized I don't have this IWA specialty group listed on here, so I need to add that to it. But when I'm not at work, I love to travel this beautiful country with my family and see how water interacts with the natural world wherever we go. So that's me in a nutshell. This is where I work in the Cypress Environmental Laboratory. This is our admin building. I'm in the front of that building. And on the right, you can see we're in North Texas there. I want to give a shout out to our lab staff. So they make all the magic happen. Like I said, I was the supervisor for the last 10 years. Now I'm the superintendent for the water system, but I'm down in the lab basically every day to some degree. We've got 3 full-time lab staff on the right, Sam, Emily, and Ben. And then we have 2 operators that work in our lab. Whenever we need assistance, basically, they work some overtime back there, and we do lots and lots of testing. We're a heavily automated laboratory. So standard methods. If you're not familiar with standard methods, hopefully you are. It's been around since 1905. It's in its 24th edition. And first, we're going to look at the different methods available in standard methods. Then we're going to look at what we've added in the last year or so that should be published online any day now. I keep waiting for the notification to see those new methods are up online. So 2150 is the odor method, and there's 3 methods in there. 2150B is the threshold odor number. And by itself, it's not really a great method as a standalone method. It gives you basically an odor magnitude. You do a series of dilutions until you can't smell the odor any longer. And it just tells you how smelly the water is, but no reference to the descriptor. 2150C covers the total intensity of odor. And in this one, panelists rank a sample against 5 different odor standards from odor-free to moderate odor. And then they come to a consensus. And 2150D is a new method that we just added. That's us or Carlos on the bottom right. He's one of Keisuke's former grad students that worked on that a bit with us when he was here training for a GCMS method as well. But in this test, we design it for small systems, specifically that don't have very advanced labs, where you can take a single standard like geosmin, and you can prepare it at 10 nanograms per liter and say, okay, this is the trigger. And then you smell some samples in relation to that single standard, and you say there's no odor, there's the same odor, or there's more or less. And if it's the same or more, that tells the operator they need to do something out in the treatment plant. So for this, all they have to do is to prepare a single standard in a 40 ml VOA vial, basically, and that's it. Smell some samples and they're ready to go. So it's a very easy, very inexpensive test for systems, even with little experience, to be able to collect some actionable data and make some data-informed treatment decisions. 2160 is the taste section in standard methods. 2160B is the flavor threshold test. And this is analogous to 2150B. So in this one, you basically do the same thing. For the amount of flavor, but doesn't really tell you anything about the flavor. In 2160C, you rank samples according to a set of statements, basically saying the water's excellent, I would like to drink it, the water's horrible, I would not like to drink it, or several statements.
Hunter, we lost your share screen. We lost your share screen. Could you share it again?
Uh-oh.
Thank you.
Sure. Let me try that. I don't know what happened. All right, can you see me again? Can you see it?
Yeah. Hunter, could you share full screen?
I'm sharing full screen. Do you
it's
you
good.
see it?
It's good now. It's good now. Yeah.
Okay, cool. I must have clicked that button at the bottom on accident. Then 2170, you're probably familiar with this. It's the gold standard flavor profile analysis. It involves a larger panel, a more highly trained panel, and it's a great method, but it is the most expensive of these sensory methods to run and maintain for a water system. So when we started to develop 2150D for standard methods, they also asked us to update this method 2110. And this is a screenshot of the method. It was only 3 sentences. So by itself, it really wasn't much of a method. So that was no good. We went in, we changed it up, and added some really cool stuff to it. We added the particulate and color wheel to it that Gary Burlingame and Andrea Dietrich have developed. Then we added this table, which I think is really exciting because if you're not familiar with these methods, it can be difficult to know which one to use for different situations. So we put some steps in water treatment processes, some objectives, what kind of data are you trying to collect, and then the suggested methods to use for those data questions, basically. So it just gives the user a little more direction that wasn't in there previously. And then we validated 2150C, which is total intensity of odor, and developed 2150D. So this is us running a bunch of unknowns, smelling the VOA vials. We did this with a lab in Arkansas, and we produced some really high precision data. So it was very, very exciting because a lot of people don't buy into the fact that sensory analyses are highly reproducible, but they are. Your nose and your senses, they do a great job telling us things that we might not be able to detect with analytical instrumentation. So we developed these. They've been voted and approved on by the Standard Methods Committee. They're just waiting on that final click to be published online with Standard Methods, hopefully in the next few weeks. When we look at the instrumentational methods, they're in Part 6000, and I'm the Part 6000 coordinator for standard methods, which basically means I'm the chief cat herder. I coordinate the joint task groups in Part 6000 for the individual organic methods, and there's 4 in there for taste and odor. 6040B's closed loop stripping analysis. This has been around since the 1980s. There's only 5 taste and odor compounds in this method. And it was widely used initially, but most people aren't using this one anymore because it's more complex, it's more expensive to run, and there's easier methods available. 6040C is in there. It's a purge and trap method, but there's really not much to it. In this method, the idea is you take your sample, purge it, you trap your taste and odor compounds in a trap, and then you release them onto a column. But if you go to this method, it tells you to refer to standard method 6200, which is a volatile organic method and doesn't really talk about taste and odor compounds specifically. So one of our next projects is to take this method and update it and to make it a true taste and odor method. We just finished the 6040D development, and we published that in IWA Water Science. It only had a handful of taste and odor compounds in it to begin with. Now it's got 20. So really excited about this because they were all from the earthy, musty, moldy category before: geosmin, MIB, a couple haloanisols, maybe some pyrazines. But in this, you insert a spemy fiber into the headspace of a sample vial. The taste and odor compounds absorb onto the spemy fiber, and then they desorb in a GC inlet and are separated in a mass spec. So we're going to look at that on the next slide, I think. 6040E is a GCMSMS method. There's only 5 taste and odor compounds on this one, but if you've got a GCMSMS, you can basically use the 6040D method with a few tweaks to run the same taste and odor compounds. So again, we're really excited about that development because now we've got these 20 taste and odor compounds from 7 different taste and odor categories. So we've got grassy, hay, straw, woody compounds, fishy, rancid, phenolics, medicinal, sweet, cucumber, sulfur, swampy, septic, sulfurous, lots of different things on there. So we're super excited about this. And that's a picture of our lab supervisor and one of KSK's grad students that did his thesis on taste and odor compounds. Part of it was on taste and odor compounds in a DPR pilot plant. So we were here training him how to do that so he could run the samples himself. In this interlab study for the development of this method, we had 4 labs involved. We had ours, American Water in Illinois, WEC in California, and Aqua, Pennsylvania. And the exciting thing about this is that we used several different kinds of instruments. We used several different kinds of columns, several different kinds of fibers, and we got great results with all of them. So it really kind of proves the ruggedness of this method. It works very, very well. The precision data was excellent. When we got the data back from the 4 labs initially, I was kind of shocked because I wasn't expecting it to be this good, because most of these compounds are not available as certified reference material standards. Basically, you have to buy pure ACS grade powders or neat liquid standards and create the dilution series on your own, and there's just more human error that can go into that, but worked very, very well. Most of the labs were able to achieve passing results for all analytes. One of the labs was kind of towards the end of the process. They weren't able to get the method optimized for everything, but overall we were very, very happy with that. And we also chose calibration ranges that bracketed the odor threshold concentrations as best we could. Another thing we added to this method that there wasn't a lot of previously published data on is holding times for these different taste and odor compounds. And what we found was for many, you don't need any kind of preservative like geosmin, MIB, raw tap water, whatever. You don't need any preservation if you can run the samples in a week or 2. Some of them have very short hold times, which is unfortunate no matter what kind of preservation we tried. But for most of them, very excited to see they don't need any extra preservation, which just makes the method that much simpler. This is some data we collected from our system during the project. So while the method was being validated in this interlab study, we collected samples from Lake Arrowhead, Lake Kickapoo, and Secondary Reservoir. Those are raw water sources. And then in our treatment plant from Cypress and Jasper, and then the 2 lagoons for the treatment plants, because we wanted to see if this method worked on real world samples, basically, and different matrices. So we got some exciting results from this as well. There were some compounds we only found in the lakes, some we only found in the treatment plants, and some we only found in the lagoons. And in the treatment plants themselves, all of the taste and odor compounds were drastically reduced by our treatment processes. So it basically validates the method a step further and shows that our treatment processes are working well in our system. So how did we get into this? Well, we've got a pretty advanced algal bloom and taste and odor monitoring plan where we use testing at the lakes, in the field, and then testing back in the lab to really put together a more holistic idea of what's going on in our water. We don't just rely on one or two things. We take data from multiple inputs to determine what's going on and what the best course of action is for treatment mitigation if we need that. So in the lakes, we use sondes to look for temp and DO and algal pigments. Back in the lab, we do bench testing for conductivity, ammonia, pH. We plate actinomycetes, which are fungal-like bacteria, and they're ubiquitous in source water, tap water, distribution system. They can produce geosmin, MIB, pyrazines, haloanesols, so they can be problematic in and of themselves. We also do a modified TON FPA where we get an odor magnitude, and we also classify the odor. So what does it smell like? Is it muddy? Is it grassy? Is it sulfurous? Then we've got a flow cam for high-speed algal identification, GCMS, like we were talking about on the previous slide. And then we do qPCR for cyanotoxin-producing genes, and we've got a light deck. And another method that's about to go to the Standard Methods Committee for approval is for the phytoxagene qPCR test that I guess the standards were developed in Australia, and it's become widely used in the US. So we're also pretty excited about that. This is a graph of geosmin detections in our water system from 2017 to 2023. And this shows how effective our program has been. The blue is the raw water samples, orange is tap water. So you can see every place you have a spike, it was drastically reduced by some means. And that might be source switching, basically turning one lake off and only pulling from the lake without the problem. And we're able to do that because we catch the problem early. Treatment measures in the plants, powdered activated carbon, potassium permanganate. We've got several different options, plus copper sulfate treatments at the lakes. And one thing we've done that I encourage other systems to do that are struggling with this kind of monitoring is we've taken every taste and odor event we've had since 2016, since this program was really launched, and we have kind of collated all the data together. So when did it happen? How long did it occur? Were we able to associate a taste and odor compound with it? How did we detect that compound through sensory testing, GCMS? What were the concentrations in the source and tap of those compounds? If we were able to associate any kind of cyanobacteria or actinomycetes or anything to those taste and odor events, any kind of organism counts, and then mitigation measures and complaints. So we can look back at this and say, okay, this happened before. What did we do? Did it work well? And if it didn't work well, we can try something different. This was going so well, at one point the Water Research Foundation called and asked us to go to New York City to help the Department of Environmental Protection evaluate their taste and odor monitoring program for cyanobacterial blooms. And New York City is one of the two largest water systems in the United States. So they've got a huge budget to pull from, a lot of manpower, a lot of expertise, but they needed help putting all the pieces together to be able to take the data, to derive something from the data quickly and make a quick decision. Because if you're familiar with bureaucracy, there's usually lots and lots of layers, and that can slow down the information chain. So that was one thing we told them: collect the data, get it to somebody quickly that can make a decision instead of going through multiple layers, because cyanobacteria reproduce rapidly and they're not going to wait on you. They're going to do what they do, which is reproduce and produce these compounds. So now getting into these non-targeted compounds that we weren't looking for, but we found because of this program, to me, this was the really exciting part. So in 2021, we identified 2,4,6-TCA in our filter media, and we determined it was caused by actinomycete production. So how this happened was in January 2021, we had a taste and odor event in one of our treatment plants. And taste and odor events are not normally common in the cold winter months here. So it was unusual. We knew it wasn't because of cyanobacteria or algae. And we collected samples from the raw water all the way through the treatment process, ran them on the GCMS, and determined it wasn't caused by geosmin or MIB, which are our normal taste and odor compounds. So how did we figure this out? Well, we determined the production was coming from our 1987 plant, and we did that by collecting samples throughout the treatment process. So we collected raw water samples. There was no odor there. We collected raw water samples coming into the plant. There was no odor there. We collected samples in the clarifier. There was no odor there. We collected samples going into the filter building and leaving the filter building, and we determined there was odor leaving the filter building, but nothing coming into the filter building. So that told us it was being produced in the filters themselves. We didn't know what it was at the time, but I was looking at the taste and odor wheel from the 1980s that was developed. It's in standard method 2170, and there's in the musty moldy category there was 246 TCA listed. We just happened to have a standard on hand, opened it up, smelled it with a sensory test along with the water, and determined it was a match. So we created a cal curve on our GCMS, and we were able to detect it in the filter effluent, but not the filter influent. Then we did a literature search online, found that it could be produced by actinomycetes. We collected samples in the influent and effluent, and we found that there were lots in the effluent. That's a picture there in the middle on the bottom photo of one of the plates that we cultured. So there was a lot of actinomycetes in the filter media. So our options were limited at the time on how to deal with it. We dosed the filters with potassium permanganate. It's not a great oxidant for haloaerosols, but it will kill actinomycetes, and that's what we needed. So we turned the filters purple. We drew the potassium permanganate down into the filters. We let it sit overnight, backwash it the next day, flush them, and then the actinomycetes went down to a non-detect. There was no taste and odor by sensory analysis and no detection by GCMS. So that's just how we tracked it to that unit process and how we dealt with it in that instance. And then a few years later, we had another taste and odor event that was similar. This time we determined it was 2,4,6 tribromoanisole, and it was originating in our chlorine dioxide generation process in the raw water disinfection line. So we had an event in January 2022, but we weren't able to determine what it was because it was pretty fast. It wasn't long lasting. And in 2023, it lasted a little longer. So again, we did what we always do. We collected all the way throughout the treatment process, and we knew that it was similar to 2,4,6 TCA, but it wasn't exactly the same. So this is a scheme of our treatment process. We've got Lake Arrowhead and Lake Kickapoo. We can treat those with copper sulfate if there's a bloom in the lakes. Then we've got secondary reservoir, which holds raw water in town. Our chlorine dioxide disinfection line. Then we add monochloramine going into our clarifiers. We can add powdered activating carbon if needed. Then we can add potassium permanganate going into our filters. And then final hit with chlorination going to our ground storage. So again, we start at the beginning. We collect samples every step, every unit process all the way through. And we found that the odor was not in the raw water. It was not in the raw water going into the transmission line, but it was in the raw water leaving the transmission line. So in that transmission line, we have 3 sample points, 3 disinfection zones. So we collected at the beginning and then each disinfection zone, and we found that the odor was in each disinfection zone. So that told us it was being generated at the point where we were adding chlorine dioxide in that raw water line. So then we went back to the lab, and we were able to identify 2,4,6 TBA as the odor compound. We did some jar tests in tap water. You can see those 3 on the left, and raw water, 3 on the right, and where we tried to reproduce this on the bench. And we did this by adding bromide to the tap water. Bromide is naturally occurring in our raw water, so we didn't need to add any there. We added anisole to the tap or to the DI water. We didn't add any into the raw water because it's already there. And then we added chlorine to both because we wanted to see at different concentrations, could we reproduce this? And we were able to do that. So those equations on the bottom right, that's what we were able to come up with as the mechanism for the production of this compound. And what that told us is that in our generation process, you have to monitor the yield and the purity. And so you have to ensure that you're producing enough chlorine dioxide to have enough in your lines when it gets to the plant to get the disinfection credit you need, but you don't want to add too much chlorine so there's an excess. You want high purity. If there's an excess, if there's too much, that's what we were doing. We were allowing there to be too much in the lines. The purity was too low, and it was causing this taste and odor problem in our water. And then lastly, before we get to some recent publications I want to share, this one is also pretty exciting. In 2024, we got a call from Virginia Tech. Andrea Dietrich was contacted by the Department of Health in Virginia, and they had a taste and odor contamination crisis. You can Google this. It was picked up by PBS, NPR, lots of different news agencies. But they had a system-wide contamination event where every tap in that system, the water coming out smelled like WD-40, and that's not something you want in your tap water. So they knew that it was possibly a hydrocarbon that contaminated the water system, but they didn't know what it was, and they were running samples in their Department of Health and their Department of Environmental Quality. Eventually, they determined. You say something? Okay. Eventually, they determined that it wasn't a primary pollutant set by the EPA, so they believed it was safe to drink, but they didn't know what it was still. So that's when we were contacted. They wanted to see if we could help. So they sent us samples on 3 different days, and we ran lots of samples over the weekends by sensory means and on the GCMS. And I don't know if you've ever done non-targeted analysis by GCMS, but it's like looking for a needle in a haystack when your haystack is full of needles. You keep finding all these needles, and you have to determine, is it the right needle? They all look alike. They're all hard to find. Is it the right one? So in September, we identified the source of the odor. There was a mineral oil leak that the water system knew about, but they didn't report to the state. Their pumps had catastrophic failures. All of the mineral oil in the pumps dumped into the wet wells coming off the river, coated the whole system, and basically caused this contamination event. So we were able to determine what it was, why it occurred, basically. And I found this on Reddit. I thought it was pretty cool. Somebody noted that we found it in Texas and told the Virginia Department of Health what was going on. So as you can imagine, Virginia, the Commonwealth, was not happy with the water system for keeping this from them. And they sent them a notice of alleged violation for that, basically saying they knew what the problem was, or they knew what the problem could have been. They knew what the problem could have been, and they didn't notify the state. And they said, despite an ongoing multi-agency investigation, they did not inform the state agency about the catastrophic nature of the pumps. And they also listed our standard method 2150D, which is the new method we had just developed for standard methods, as the way that we identified this odor. So what we did when they sent us the samples, we weren't able to determine it by GCMS because there's thousands of different hydrocarbons that can be in mineral oil. But we did take the sample of mineral oil, we scorched it on a hot plate, and we did some dilutions from that, and we were able to come to a match using 2150D to their water sample. So sensory analysis wins again, and it told us that it was a match using our noses. Next, I want to share some recent publications before I wrap up that I think are pretty exciting. If you're not familiar with these, they're all great resources. American Water has a series of papers from 2021, 2023. There's another one on the next slide as well. But Sashira Poshiraju and her team, they were the ones that developed a taste and odor compound for 18 taste and odor method for 18 taste and odor compounds by GCMSMS. And they're the reason that we did our new taste and odor method for 6040D for GCMS. Because I read this paper several times and I thought it was great, but most water systems don't have a GCMSMS because they're too expensive. So one day I was driving down the road and I got to thinking that the separation is going to be the same, right? In a GC. If she can separate those 18 in her GC, I can separate them in mine. The question is, she's got a triple quad mass spec. I've got a single quad. Can I detect them at the same level she was able to? So I emailed her and we started working on this method development together. And then we pulled in a lot of others, including folks from American Water and some other labs. So that method really helped the development of this new standard method. They also went a step further and they looked at the treatability of those 18 taste and odor compounds by different kinds of powdered activated carbon and by different types of oxidation. So you've got chlorine, permanganate, and ozone. So this is exciting, I think, because if you can identify the taste and odor compound in your system, you can now go to their papers to see what kind of pack is best to use and what kind of oxidant is best to use against that taste and odor compound. Then I think Jen is on the call or on this webinar, but there's some really cool stuff coming out of University of New South Wales. In 2022, Jen did a review of biogenic sources of taste and odor. It's an excellent source. It starts in source, goes to in-plant sources, and into distribution. 2023, there's a publication on taste and odor in mixed water samples for systems that don't have a single source, either a raw water source or they mix even tap sources. And just recently, I believe a month or so ago, they published a meta-analysis of biogenic odor management, which is a really exciting paper. You can access all of those online, or you can shoot me an email and I can send you a copy of those. We've got several that have come out in our lab recently on our monitoring program, and then how we use the different steps in our monitoring program, looking at some different data we collected. I talked about that one on the bottom already. In 2022, we did a review of taste and odor production and control in drinking water based on pH. So we basically looked at the literature, and anywhere we could find how pH affected taste and odor, we try to include that in here. And we structured it so you start with surface water, look at wastewater impacted source water, groundwater, then treatment processes in the distribution system, and in lab analyses. And one of the funny things in this is we talk about the need for new testing in the lab analyses, and then in the next 2 years we developed those methods based on the need that we found in this paper. For those systems that use flow imaging microscopy for algal bloom counting and cyanobacterial counting, we found that a lot of systems want to use it, but they don't know how to use it effectively, I guess. So we got together with several other systems and we wrote an article in OpFlow on how to establish trigger levels. And so this is basically going to be different for every system. My trigger levels work for me in my source water. Your source water is going to be different. It's going to have different chemical compositions. It's going to have different inputs, different temperature, different depths, different clarity. So you have to do a lot of baseline monitoring to set those numbers where you can look at and say, okay, if this is my baseline, this is where the problem is, I want to set my trigger here. So we just talked about in that how the different water systems got to those points in their systems. And we also ran one in Journal AWWA in 2024 on using flow imaging microscopy as a larger facet of a algal bloom monitoring program, like I was talking about earlier with SONS and qPCR and different things in the laboratory. And then that article on the bottom, that's our, I guess our biggest article on our system where we look at each individual piece, and it's got all the data from all those taste and odor events and how well they work for us in our system. And like I tell everybody, that's our data. It works for us. You can use it as a framework, but you have to do the work to create your own baselines to make it work for you. If you use our numbers, it's not necessarily going to work, but you can use the framework to help develop your own numbers, your own triggers, your own monitoring frequencies to see what you need to do for your systems. And then more recently, we've had a few come out in the last year or so on sweet and salty taste, difficulty with describing odors, where we look at how water systems need a set of criteria, or a set of descriptors in place to give to the public, because a lot of times you and I might describe something differently, even though we're perceiving the same odor or taste. We just don't put the right descriptor on it. And then we've been doing some work with water safety planning, looking at water quality aesthetics, And so these clips on the bottom here, they came out, I guess, late last year in the Journal of Water and Health through IWA, where we looked at assigning risk scores and hazards that were aesthetics, looking at how to mitigate those hazards and then how to verify the effectiveness of that mitigation. So you can apply this to anything in your water system, but nothing had really been done well for aesthetics. So we wanted to put an example out there of how we could do that in our water system. And then that top right article is an update on all the different taste, and odor, and appearance methods and standard methods, and how you can use them in different scenarios. So lastly, these are some 2025 publications that have come out or are coming out. On the bottom right, we've got our GCMS method that just recently came out for solid phase micro extraction that I was talking about. Has the 19 taste and odor compounds plus the internal standard, so 20 total. Top right, that one's coming out in June. It's on smoky taste and odors. We've been having lots of big wildfires in the U.S. and California and Colorado and other areas. And so we get a lot of questions on smoky compounds in water, but there's not a lot of funding for that because it's intermittent. It doesn't occur all the time. But when it does happen, people want answers. That picture from the top right, that's from a case study article we've got coming out in July, where we looked at case studies from different water systems and how they proactively monitor and characterize aesthetics. And we did a mini flavor profile analysis at WQTC 2023, I believe. And that's a photo from that where we trained people in the workshop on how to set up a rudimentary FPA in their systems. And then down there on the bottom, this one's coming out in October on how to take non-certified reference materials. So you've got pure standards, you don't have a set concentration. How do you prepare those? Because oftentimes we find people in water systems don't necessarily have a chemistry background. I didn't when I started, had to learn all this on the fly. So we want to kind of put a roadmap out there. How do you take these pure standards? How do you do a dilution series, make a known concentration, and set a calibration series from that? So really excited about those because we spent a lot of time doing that internally, and now we can help others with that. So that is what I've got to share on updates to taste and odor methods in my neck of the woods here in the U.S. I guess I'll turn it back over to y'all and we can move on to questions.
Thank you very much. This is an excellent presentation. You kind of give us, the development of last few years about this field in the US, I guess. Thank you very much.
Yeah.
So I think we still have 20, 25 minutes for discussion. So please raise your hand if you have any question you'd like to ask out to the distinguished speakers for today. Oh, yes, Niels, I see you.
Yeah, thank you. Maybe mainly a comment. Hunter, I'm impressed with all the work you do. I know how complicated it is. So also the intercomparison between different laboratories. I was involved in a similar study for another compound, and that was completely a mess. So I'm really surprised you can. So you send 10 nanogram per liter samples, I suppose, and almost between 90 and 100% were correct when you got the results. So that was one comment. The other comment, there were some real high deosmin levels in the lakes. You showed a study earlier. I think that's unusual in at least the lakes I have studied in Denmark. The level is much lower. Have you any comments on why? I think you had 500, 600 nanograms in some cases.
Yeah, we've had even upwards of 1,000 nanogram per liter MIB, and it gets so bad here that sometimes you can smell the lakes before you even get to them. You're driving up to the lake, you can't see the water yet, but you can smell that dirt in the air. It's really, really bad. And part of the reason is because where we are in North Texas, it can get very, very hot in the summer. Our lakes aren't very deep. And if our aeration systems aren't maintained well, if the lakes don't stay well mixed and they start to turn, it can cause problems. If we don't catch the blooms quick enough, it can cause problems. And in one of those, at least, the aeration system was down and we weren't able to get it fixed in time. We did multiple treatments at the lake that summer trying to kill the bloom with copper sulfate, but we just couldn't get it under control. So in that instance, we were able to switch to our other lake, Lake Kickapoo, and draw water from there. So that's why the tap concentration was so low. We wouldn't have been able to treat that out in our conventional treatment plants, even with PAC. You can only do so much. So it just depends year to year. Some years are good and some years are really bad if the lakes aren't, if we don't maintain control of the lakes.
At what level does consumers start to complain if you consider jasmine? We have this limit. I think I may be able to detect it from about 10, 15 nanogram per liter. But are consumers more aware of the off flavor?
Yeah. Normally, when we hit around 10 to 15 nanogram per liter, we start getting complaints. Anything over that, we get a lot of complaints. And growing up here, we didn't have this program in place, so my whole life it was just normal for us to have odors in our water, and so the people that have been here a while are used to it, but the people that have moved in recently or younger, they're not used to it, so they're not happy with it. So we really try to maintain that threshold. So if we start seeing the numbers creep up, we go ahead and turn on PAC proactively to keep those levels down. And we do treatments out at the lake early to keep them under control.
Thank you.
Yeah, I actually also have an experience in like when I visited South Australia, actually the jasmine concentration in the water always around 10, 20 nanogram per liter, and I can clearly smell that. But my friend there they kind of get used to it already, so it's probably similar situation. It's just like the hunter mentioned. Yeah. And I also have one experience when we took a sample in Philippines, that one of the big lake over there in Dagunante Bay, the concentration of MIB we detected could be as high as 2,000 nanogram per liter in the water. So you actually smell from very far away. When we brought to you, even you stand maybe 100 meters away, you can probably smell that the MIB odor over there. So.
That's very bad.
Yeah. And they grow fish in there, so that link back to Niels' research that they grow the tilapia in the lake. So obviously you can smell the odor when you eat the fish. So one question for Neil, what is the the concentration people usually detected for the fish, for the jasmine fish?
Yeah, for jasmine, we found out that the level, at least for freshwater fish, is about 250 nanogram. And that was based on, we had about 200 fish. A portion of them were tested by a sensory panel. And when they could not taste any off flavors, we saw that was about 250, 300 nanogram. And when we look back at what was the concentration in the water, it was about 10, 15 nanogram. So I think that could be the rule of thumb for fish producers. And what fish producers do in Denmark, there's a company offering for about 125 US dollars. They will analyze a water sample. So the fish farmer can send in 5 or 6 water samples and get an idea on what the level is. So I think they are aware of it, but otherwise they do. I sometimes go to Arizona. I know they put a fish in a paper bag, put it in the microwave oven, then take out the back fin bone, and if you can taste jasmine, then the fish is not good for eating. So there are some tricks a fish farmer can use, because they don't want to spend money analysis of geosmin. And typically when you visit a fish farm in Denmark, they would ask, could you please take some water samples back and analyze the geosmin MIB content? And sometimes we can do it, and other times we say, okay, you have to ask a commercial company. This company, Fanu, also offers analysis of fish, so they have a standard for geosmin in the fish flesh, but that's more expensive, and I doubt how reliable these methods are. I don't know, Hunter, are you using twisters? You know, that's a Swiss, it's a Swiss company, Gerstel. They made some little magnets covered with silicone material, whatever it is. But to be able to buy them, you should buy the autosampler. But it's very convenient. You can put them in water and just let them sit in water for some hours. You could, in principle, hang them in the air. And they have also been tested for, if you homogenize a fish, then put these little 1 centimeter long twisters in the fish soup you get. But then the lipids is of concern, because lipids will stick on the outside of the silicone membrane. But that's, I think that's the new way here, at least in Europe, using these twisters. But it's a Swiss company, and they have a monopoly on this. So that's that. Again, you have to buy the autosampler, but if you know somebody having the autosampler, then you can ask this person to buy the twisters, because it's just a small magnet. So
maybe it is a good a new market for Hunter. You know, maybe can help the aquaculture industry to do the analysis, because usually the aquaculture industry sometimes the farm are small, so they don't have enough kind of a instrument to do the analysis. Yeah.
But is this twister method, is it known in Asia, you think?
We actually do the analysis, but we didn't use the twister. We just try to use the extraction, like methanol or other type of chemical analysis to do. And one we have analyzed some sample from Thailand and also from Taiwan, and we do find some geosmin, or it might be problems in the fish meat. And actually and this will link back to Hunter's presentation about the pH kind of effect on that geosmin, or it might be or other taste and odor compounds. And actually I have some impression that, because if you go to Thailand, when they cook the fish, they always make lemon fish, so make the pH lower. And then you cannot smell when the geosmin might be concentrated in low pH, so that will kind of make the fish more tasty without any musty odor. So that's probably one of the reasons they cook it in that way. So I don't know, maybe Andre can make a comment about this part.
In Denmark, we have we call them put and take lakes, where somebody, maybe are they familiar to you, Hunter, in Texas? You put a lot of rainbow trout, I don't know, 25 centimeter in the lake, and then people pay $20 for fishing for one day, and when they catch the fish, they are usually very off flavor, contaminated, because I don't know, the fish like to stay at the bottom. But that causes an issue. So when you have paid a certain amount and taken your son to one of these lakes just for fun, and you catch a fish that is unedible, then it's not a good sense. But in Texas, don't people go fishing in the reservoirs?
Definitely. Lots of catfish, and the catfish here will taste pretty muddy a lot of the time. Bass are usually cleaner tasting, but muddy flavors in fish, they're a problem here too.
Did you ever look at Hunter, at myxobacteria, slimy bacteria on surfaces?
No. In at one of our reservoirs, we typically have sustained geosmin even in winter when there's no cyanobacteria that we can find in the water. and the water is also very turbid. It's got a lot of clay, a lot of sediment in the water, and so we're assuming that there's some kind of bacterial growth, slime or something on the bottom. Light doesn't penetrate more than a foot deep very well in this lake, so we don't really know where it's coming from, but we're assuming it's bacterial.
Yeah.
So Hunter, you mentioned about that you're still using the copper sulfate in your reservoir. Do you have any kind of a limitation or any kind of a constraint for using the copper sulfate?
No, not from the state. We just have to make sure it's food grade. We keep our dose below 1 milligram per liter just to make sure we don't have a fish kill. So we want enough to kill the algae and cyanobacteria, but not enough to harm the wildlife, essentially.
So what kind of copper sulfate do you use? You just use the regular copper sulfate, or use the kind of a new formitter, or?
We've tried 2 different kinds. We usually use bad copper sulfate. We mix it in a tote on a boat. We add citric acid to lower the pH, make it more soluble, so it gets into the water, dissolves more easily. And we've also tried a liquid copper sulfate as well. We've used here at the plant some, but normally bagged. It's cheaper.
Yeah, your new method, especially the 60-40, I'm very impressed. So really look forward to see the new publication coming out.
Yeah,
from the standard method. Yeah,
we're excited. We're excited about it.
Yeah. Do we have any questions from the audience? Miao, yes.
Hunter, one little question about the detection range of the other compounds. I see that you established the method with the calibration range in hundreds nanogram or some cell ethers. So how do you consider this? And I see that in the fresh water, the occurrence level for the dimethyl disulfide were undetected. Actually, in our investigation in China, we found that cell ethers like the dimethyl disulfide and the dimethyl trisulfide usually co-occur. So could you give some comments about this? Yeah, thank you.
So when we started, first thing we wanted to do was to see if is my mic on? Can you all hear me? Yeah, okay.
Yeah.
We wanted to see if we were able to detect the compounds at all. So we started with high concentrations, and then we worked down. We looked at each compound. We looked at the odor threshold concentration, and we wanted to get as close to that as possible. Some of them we weren't able to get down low enough to that odor threshold concentration. We were a little higher. But some of the compounds we were in the the 0.1 part per trillion range, upper PPQ range for several of these. We wanted to bracket them as best as we could so that water systems would be able to detect early and before it became a problem. So that's how we established those. And they're listed down here in this article. I can't turn this. I have to download it first. So whatever the odor threshold concentration range was, that's how we ended up choosing these calibration ranges. And you can use whatever you want. We just wanted to get as low as possible and within those ranges for this testing. What was the other question about the sulfides?
Sulfide, yeah, the methyl, the MTS.
Okay. Yeah, so we didn't detect any in our tap water, but we did detect it in the raw water, the lake water, and in the lagoons. And we've also detected DMS and DMDS and DMTS in reuse water. We've done testing with Keisuke Ikehata from Texas State, we found that in their wastewater effluent.
So
Does that
your
answer your
source
question? What'd you say?
I just want to ask, you mentioned that you detected DMS, DMTS in your source water. Have you tried to match this together with your FPA kind of a category to identify if they match the odor?
No. So we've only found it down around 10 to 15 part per trillion. The odor threshold's right at 10. That's what's published. I don't smell it at 10. So
okay.
We haven't been able to detect it there with our nose yet, I guess.
We can smell DMTS at 1 nanogram per liter in pure water.
So we haven't done the testing in pure water. Our lake water normally smells very muddy and very fishy, and I'm assuming that would mask the sulfurous odor if it's there.
I think the other possibility is that because maybe Chunmiao's panel, are younger, much younger. So usually, the younger you are, the lower detection limit you can go down to. I think, for example, my detection limit is much higher than my students' detection limit. So. No, just kidding. Yeah, okay. So we actually we also found some DMTS and DMDS in our source water, but the concentration is not not very high. But and we actually find out maybe the more possible one is maybe mercaptan or hydrogen sulfide. I think. Yeah. So we're still trying to investigate in some of our source water for the potential source. Yeah. But DMTS and DMDS are quite common in our urban water, like in the city, near the settlement area. So
okay.
Do we have any other questions?
Maybe before we turn off, are there any updates on the conference this summer? That's completely different topic, but before we leave.
Yeah, I just discussed with Chunmiao that they are still trying to finalize the website, and we'll try to email out soon to everyone. Am I right, Chunmiao? Yeah.
Yeah.
So the date is is fixed. So please reserve your dates, and then you maybe you can also contact with the your partner in China about the fish farm kind of a Beijing type of things. Then we can have a discussion try to include that into the technical trip. Yeah. And we also have Professor Ikihata online. Professor Ikihata, welcome on board. Yeah.
Oh, hi. This is Keisuke. Sorry, I was. Well, it is 7:30 now here in Texas. I live in Texas. No, it's too close to Hunter, but we can meet driving 5 hours or so. Yeah, it's a great webinar. Thank you for putting this together, and I'm excited to join this group.
Thank you very much for joining us. Yeah, welcome on board. Yeah.
Thank you.
So any other
questions? By the way, yes. I don't remember exactly, but when my student and I were working on the taste and odor of reclaimed water, we must have tried DMS or DMTS smelling in the pure water when, but I can't recall how low that concentration it was where we could detect it. My student was reasonably young. I'm 51 years old, but he was 20-some. So I cannot recall. I think DMTS was pretty hard to smell based on my experience, but yeah. Okay. I mean, I'm not the best person. Okay. Just to give you some perspective.
Thank you very much. Yeah. Okay, any other questions or comment? Yishen, you have any other?
I have one question for Hunter. Is that you have talked about the there's some solvent in the treat water. So I think we have also met this kind of problem in Taiwan. So do you have any experience about when the pure treated water have some um, experience to find out any kind of hints or any evidence what kind of compounds will is dominant from in the water, or where's the problem comes from in the water treatment plants? Do you have any ideas about this?
I think the easiest thing to do is basically what we did when we were looking for those non-targeted compounds. We didn't know what they were. We just collected samples all the way throughout the treatment process. 200 mils, we heated them up to 60 degrees, and we smelled the sample. And we started at the very beginning, then worked our way through the plant until we could smell it, basically. And so that would tell us what process it was originating from. If it's not in your raw water, if it's not in your clarifier influent, not in your clarifier effluent, you just keep going until you finally smell it for the first time. And that narrows the point down where it's being produced. And then you got to try to figure out what it is, and that's a whole different can of worms. You can run non-targeted scans on a GCMS, but it's difficult to find what you're looking for because you don't know what you're looking for. You're basically searching hundreds of compounds to see if they could be the compound. What are their odor descriptors, and then try to order standards to see if they match. So it can be a long process.
Yeah, because we made this kind of problem several times, and we don't know how to start and how to analyze that samples, because we also did the same way like you did. We heat the water and smell, and sometimes it's quite strong from the just sampling from the clean water. So there's kind of a really strong attack to your nose. So you smell there's kind of some solvent in the water treatment plants. But I just suspect that it may come from the coagulants and the chlorines combination just after the water.
Yeah.
Thank you.
Yeah.
So Hunter, you have experience about your plastic odor?
About what odor?
Plastic, like glue, plastic, type of odor.
Not really. I would make sure when you're collecting samples, collect them in glass. That way, you know if it is a plastic odor, is it coming from the water itself, or is it coming from the bottle? So if you collect it in a plastic bottle, it's probably going to be the bottle. But we've never done any testing for plastic specifically.
Okay.
It might be some finals, I think, for the plastic odor. It might be from the pipe that transport the water.
What was the compound again?
Some finals.
Okay.
Right.
Okay, we'll try to check it again. We suspect it's actually coming from the coagulant, and and something combination together with chlorine. Yeah. So. Okay. Do we have any other questions? I think it's about 25 minutes, for discussion. Okay. So if no, please join me to thank Hunter and Niels for their excellent presentations. So we'll try to. Are we okay? To share the slide. To share the video in a group. Okay.
Fine with me.
Okay.
Sure.
Okay. So please join me to thank them again. Two excellent speakers. Thank you very much.
Okay. Bye-bye.
Okay. So see you next time for the meeting. Thank you very much.
Yeah. Have a great weekend. It starts here.
Yeah,
Thank
you
you.
too. You have a great weekend. Thank you very much. Yep. Thank you. Thank you, Samuel. Yep. Thank you, Hunter. Thank you, Neil.
Niels,
And thank you
Hunter,
all the
thank you.
audience. Thank you very much.
Okay, thank you. See you.
Thank you. See you.